Well, welcome to this 378 review. Thank you all for coming. Once again, sorry about the room mishap. Hopefully, we don't get kicked out of this one. I am planning on this just being about an hour, hour and a half, maybe. If you need to leave throughout, it's okay. Feel free to head out. But let's go ahead and get started. So what I have prepared for you guys today is I just have some review material. I'll just go through kind of the important points that we've talked about thus far that you're going to be tested on. And then also I have some like practice problems as we go through to do with you guys, because I know it can be difficult sometimes to just get all the material and not have practice. So we'll do that simultaneously. And then the practice exam we can also go over at the end if we have time. I think Peter and Spencer went through the practice exam in their reviews as well. So you can look out for that. But we'll definitely go through at least the true or false, because I think a lot of the time, especially on these kinds of exams, I don't know how you guys feel, but the true or false, I think, are sometimes the hardest part, which is ironic because you have a 50-50 shot. But you're also supposed to explain, right? So there's some points there. But let's go ahead and get started. Feel free to raise your hand, interrupt me if you have any questions throughout. And we'll go ahead and start. So let's see. I think the first thing, so I think lecture 7 was on like correlation and covariance, right? So a few important formulas to know would just be like, what is the formula for covariance, right? So if I have the covariance of x and y, that's sometimes denoted as sigma xy, right? And this is equal to the expected value of x times y minus the expected value of x times the expected value of y. You might see like this as like mu x, or this sometimes as mu y. It's the same thing in this case. So that is your covariance. And then your correlation is indicated by this P looking Greek symbol. It's called rho. And so that's equal to just your covariance over the standard deviation of x times the standard deviation of y, right? And if we remember, how do we get standard deviation from variance? We just square root it, right? Because all variances is your standard deviation squared. And so you might see this as like sigma underscore y, and this as sigma underscore x to denote the standard deviation of x and y. And this is sigma xy, like we said. So if you see sigma squared, x, for example, this is the same thing as your variance of x. So don't get startled there. And that's kind of the important formulas you need to know when it comes to correlation and covariance. Your correlation is always going to be, another important thing is your correlation is always going to be bounded between -1 and 1. So if you have 0 correlation, what is the correlation coefficient going to equal? 0, right? And if you have a perfect correlation, perfect positive correlation, what's the correlation coefficient going to equal? 1, exactly. And the opposite for a perfect negative correlation would be -1. So your correlation is kind of just a scaled covariance, right? It's just we're scaling the covariance by the standard deviations. And so it's basically just giving us the idea of if x increases by 1, for example, like what's the correlation in y, right? So that's kind of the intuition behind what covariance and what your rho or your correlation coefficient is. Covariance is also just the idea of how do x and y vary together. So if we think of variance as like the spread of the data, if we like think of the variance of x as like how farly distributed is x from the true mean of x, kind of that spread is the variance. You can kind of think of that similarly with like x and y together. How do they vary? And that's what covariance is. And so those are some important things. Some quick little tricks to remember, these are probably really important, is that the covariance of ax and by, if I say that a and b are constants, Does anyone know what that equals? Any brave souls? Okay. I will tell you happily, it is AB covariance of XY. So we can pull out the constants in front of the covariance, right? And then an important thing to know about the correlation is if I have the correlation of, for example, X 100Y, does that change my correlation coefficient of just X and Y? No, right? So this is the same thing as just the correlation between X and Y. So I can totally see you having maybe like a true false question or something like that on this, but I'm not sure. So that is just some overview behind covariance and correlation. Next, hopefully we'll get through like the content review pretty fast. Next, I wanted to go through like what a PDF is versus what a CDF is. So I've like talking to students and like lab hours and stuff. A lot of you guys tend to, and me, including me, like it's hard to kind of differentiate between what is a PDF and what is a CDF, right? So we're just going to go through this really quickly. I think it's very valuable as most of this test, you're probably going to be dealing with a PDF or a CDF in some way, right? So a PDF, does anyone want to give everybody else a definition of what a PDF is? So a PDF, and that's okay if no, I can go through this, but I'm going to keep asking you guys questions. It'll give you opportunities to share and reflect on what you know already. So a PDF is just going to be your probability density function. So if I have some like distribution like this might be some value, right? And this might be like some other value. We'll say 1 and x2. Which value is more probable to occur, x1 or x2, based on this PDF? X1, right? And so the PDF is just showing out of all the values that X can take on, this random variable can take on, like which have the most likelihood, right? And so it measures the relative likelihood of different X values. And that's what a PDF is. So a few things to know about PDFs. One sec. Okay, a few things to know about PDFs is that the probability of some moment, I guess, some random X is going to equal 0. So for example, if I just take the probability of x2 of this X value, it's going to equal 0, right? Because we're talking now instead of discrete, we're looking at continuous functions, right? And so that means they're like the area below it is kind of, it integrates to 1, but we're looking at like an infinite range, right? There's an infinite amount of numbers or probabilities of X values in between there, right? And so that's why when we take the probability of just one X value, it's equal to 0. So that's something important to know about PDF. Another thing, like I mentioned, is that a PDF, like if we integrate a PDF on the bounds of integration, so if X, for example, if X is contained between 0 and 1, and I integrate from 0 to 1 my PDF, that should equal what? To be a valid PDF, what should it equal? That's 1. Exactly, yeah. Because all of this area, if these are my bounds of the PDF, all of this area is the probability, right? So if I want to find the probability of some range, if I want to find the probability of x1 to x2, right? If I want to find this and I have a PDF, I need to integrate, right? From here to here along the PDF. And it's basically just taking all those little moments that on their own have a probability of 0, adding those all up together, all those infinite points, right? Because you have an infinite amount of X values between like 0.1 and 0.2. You have 0.111, like, you know what I mean? So when we integrate, instead of doing a summation like in discrete, when we're doing discrete functions, and we have a PDF, that's going to give us the probability. So in theory, if we integrate from the one bound to the other, remember the law of total probability tells us that like the probability of an event occurring like all the time is going to be 1. So this should equal 1 if we integrate it. And so like if we integrated from x1 to x2, for example, the PDF, this would equal the probability that x1 or that some x value lies in between these two, right? So we'd have to integrate it. Does that make sense to everybody? In contrast, the CDF is pretty fun and very useful because the CDF is just, it measures the, I'll write it out so you guys have it, but it measures cumulative, I think that's how you spell it, probability. So for example, it'll give, like if I have f of 2 on some distribution, that's giving me on the PDF, if this is 2, that's giving me the probability that some value of my random variable x is below or equal to 2. So it's all of this probability, right? All this area under the curve. So it's a cumulative probability. We're taking all the probabilities up to a certain point. So it's a little different than a PDF. So like if I were to think about them both on a graph, for example, this was like probability. Hopefully I'm doing this right. Yeah. And this is like the value of x, right? We're looking at a random variable x, meaning at random, this x could be, if it's bounded between 0 and 1, for example, it could be 0.5, it could be 0.75, it could be 0.3, right? At random, it can take on an infinite amount of values, which is why it's continuous. So random variables, in this case, we can show by doing this distribution. So my PDF might look something like this, whereas my CDF might look something like this, if this is 1. Because as I move along, right, the values of x, as I'm increasing whatever value it is, if we go back to this over here, this little drawing here, the probability below this x value, let's say, I don't know, -2, is not very much. And then as I go to -1, it gets bigger. As I go to 0, it gets even bigger, right? Until I get to this, I don't know, 3, for example, like that is going to be equal to 1. So the cumulative density function or cumulative distribution function is just going to be approaching 1 as you increase the x values, because all a CDF is giving you the probability below a certain value that x can take on. A PDF is showing the distribution of those. So they're different in that way. Does that make sense? Welcome in. Does anyone have any questions about PDF versus CDF? No? Yeah.
Can you just repeat that last phrase you said?
Yeah, let's see if I can remember. So a PDF is just showing like the distribution of likelihoods that different values of x can take on for the random variable x, whereas the CDF is a cumulative like probability. So it's showing that all the probabilities of the x values below a certain x value is what the CDF is showing. So if I'm looking at f of 2, for example, right, we're looking at the probability that x takes on the value of 2 or anything below that. Whereas if I do the same thing with like my PDF, this is going to equal 0 because the probability in any given moment or any value that x can take on with an infinite amount of values that x can take on is obviously 0, right? Because it's just so low. And so for a PDF, I would need to like integrate over some range to find some probability. So like, for example, this, right? If I want to find some probability of some range, I need to integrate. Whereas a CDF, I can just say, if I have this distribution A and B, and I want to find this probability, I would just take f of B, right? Which is going to give me all of this minus f of A, which is going to give me all of this. And what I'm left with, those like cancel out. What I'm left with is just this range, this probability, right? And so that's something I would use doing the CDF, whereas this is like something I would do using the PDF to find the same probability range of a certain range, right? And so that's kind of the difference. So this would be like my CDF and this would be like my PDF. Does anyone know how to get the CDF from from a PDF? Say on the exam you're given some PDF and the problem says find the CDF for this given PDF. How do we do that? How do we go about doing that? What do you think? Well, I'll give you a hint. If to find the same range of like values that X can take on their probability, if on a PDF I integrate that over that range, and on a CDF I just subtract, what might we need to do to the PDF in order to get the CDF? Here it looks like I'm integrating to get the same thing. So what might I need to do? Anyone know? That's okay. So it's not too bad. All I got to do is integrate. So my CDF, which usually you'll see like big uppercase Fs, my CDF is just equal to the integrating my PDF. So this is going to be my PDF. So similarly, the PDF is equal to the derivative of my CDF. And more specifically, the bounds of integration I need to have is going to be X. And then this is just going to be like your lower bound. So in this case, we did like 0 to 1. This would just be 0, right? And that's when Dr. Price did the whole X tilde thing. And all he's doing is trying to differentiate between the X's. So if I had some PDF function that was, I don't know, this is 100% probably not a valid PDF function. I'm just writing something. But if I have like X squared minus Y as my PDF function, in order to find the CDF, I would just integrate, and let's say X and Y are bounded from 0 to 1, for example. My CDF would just be 0 to X. And then I would say X tilde here. Let's actually not do Y because that's confusing. Also, it's just a function of X, so that makes no sense. Anyways, so I would just have this tilde here to differentiate between the X's, because all that's going to happen is when I integrate, I'm going to substitute X in for X, but they're like different X's. Does that make sense? And so you can put the tildes here just to like kind of understand that. And so here I would have like X tilde, take the antiderivative, right? Evaluate it from 0 to X. And then I just plug in X everywhere there's an X tilde and 0 everywhere there's an X, subtract them. So I just have like X cubed over 3 minus 0 cubed over 3, which is just equal to 1/3 X cubed, right? And that would be like my CDF, for example. So all you have to do to find the CDF from your PDF is integrate up to X, which makes sense intuitively, right? Because what is a CDF? It's just showing you the probability of an X value and below, like of random variable X taking on a value of 5, for example, and below. So we're just going to take the lower bound of integration up to some X. We don't know what it is, right? So that when we take f of 2, for example, it's giving us the probability below this X value of 2. When we take f of -1, it's going to give us the probability below -1. So it's accounting for this X, whatever value it can take on, whether it's 2 or -1, you're integrating from the lowest bound to that X, which is just this area, this range that I'm coloring in here, right? Does that make sense to everybody?
So on the test, are you like just gonna give us like, are some of the examples gonna be like, you'll just give us the PDF and then all the either or, and then we just have to solve for the other, or?
Yeah, so I can, yeah, good question. I can totally see, I think on the practice exam, there's a question that it gives you the PDF and it asks you to find the CDF. So that's usually the case. You could totally have a question that gives you a PDF and has you do a few problems. And one of the parts might be to find the CDF. So all you would do is you would integrate from the lower bound to X over X of this PDF. Does that make sense? And then that would get you your CDF.
With some of the other examples, are they gonna be asking for other stuff, like when we need to find like the mean and stuff? Is that gonna be with like a PDF? Is that?
Yes, for sure. And we'll go through that too. But yeah, that is for sure. I can see you getting like a PDF and then you have to solve like a joint PDF, let's say, and then you have to solve for K, and then you have to find the marginal distribution or marginal density functions, and then they'll have you find the expected values, and they'll have you find the correlation coefficient, like that one class in class activity we had, or one of your homeworks also has a problem that has you go through all those things too. That's a very probable thing that you could see on an exam or the final or something like that. But yeah. All right. So that's PDF. Yes, question.
This might be strange and not relevant question, I guess, but we've like visualized all of this by like we have the line and we color everything into the left. Would there be an instance where we would instead color everything in the right?
That's a good question and very relevant question. Yeah, because I have it pasted here. Do you guys remember this lovely table? Hopefully you recognize it a little bit from the homeworks and stuff, because you probably will be using this on the exam is my guess. This is the CDF of a standard normal, but instead of giving the probability below a certain X value, as you can see here, right? It's giving you the probability above some Z value. So that is an example of where you would see that. And it's the same thing, right? At the end of the day, it's the same thing, but you'll just have to know, is it giving me the probability above or below? Usually, I don't know if in every class or every instance, but in this class, usually if you see CDF, it means probability below. By definition, that's what the CDF is. This is just a weird table that shows the probability in the right hand side instead of the left. And that's just because that's how it is in your textbook. I think Dr. Price in class said he prefers to use tables that do it the other way, right? The way we're actually solving for CDFs, but this does it the opposite. So good to keep that in mind when you're solving problems with this. Yeah.
On that, would you just do like 1 minus your Z value, and then that's the one that you're looking for?
Yeah, exactly. Yeah. Or you can just think, yeah, exactly. You can, whatever the probability below this is just going to be the probability of 1 minus this, right? So you're exactly right.
The Z value is like a negative number in that case.
Good question. I have some practice problems like that, but we'll just talk about that. In a standard normal, there's symmetry, right? And so if I have this negative Z value, this area is going to be the same as this area, for example. And so you can kind of just say, if I'm trying to find this area, I can just try to find this area because this table doesn't give you negative values. And so by symmetry, you can just do the opposite. But we'll have a practice problem like that too. But good question. Yeah. Okay. How are we feeling about CDF versus PDF? Do we feel good to kind of move on? We got a lot more to go through. So if you have questions, feel free to interrupt. So this time is for you guys, right? So next thing is we went over uniform distributions and normal distributions. So uniform distributions are pretty straightforward, right? So we won't spend too much time on them, but if you remember, like a uniform distribution is going to be something like this. You'll have some K value, some constant, some bounds, some A to B, and it's uniform, it's flat across. So the probability is the same for all these values. Quick shortcuts you can use. If you do our general definitions anyways, you'll still get these same answers, but some quick shortcuts would be the mean. It's going to be a plus b over 2 always. And then your variance, it's going to be b minus a squared over 12. Okay. And then we have our normal distribution. And so that, sorry, this uniform distribution usually will be notated like this sometimes, which means the random variable x is uniformly distributed. So once again, what is a random variable? It's a variable that can take on random values. And so what are those values that this variable is taking on at random? Well, they're distributed from A to B, and they're all equally likely, right? So it's like that equal plot plane. So that's what this is saying. Okay, and then a normal distribution, you'll see if x, the random variable x is normally distributed, you'll see something like this, where this is the population or the true mean, and this is your variance, right? And those usually look like what we're used to seeing, kind of like a bell curve. Forgive my drawings if they're not the best, but also I would recommend that you guys just draw on this exam. If you're ever like confused, you're like, what am I needing to find? What am I even talking about? If it works for you, drawing helped for me when I took this class. So, and that still obviously helps. It just helps me kind of know my thoughts. But this PDF is this big, huge, I don't think you guys need to know this, but it's like this big, huge, ugly thing to look at, which we talked about in class. This is the PDF for a normal distribution, right? So if you see that, that's what it is. Your mean or the expected value is just going to be mu, right? And the variance, which is just going to be the expected value of x squared minus the expectation of x squared. It's just going to be sigma squared, which we can see here and here, right? There's your normal distribution. And something cool we can do with normal distributions is we can standardize things. So if we have a bunch of different normal distributions with like different means, different variances, right? One thing we can do is standardize it. And that's super cool because it helps us compare things from different normal distributions, right? And so this table, I'm going to scroll down, I'm sorry, but I'll be back. This table right here, if we can see, is a standard normal distribution table. So if we standardize any PDF we're given, then we can use this table to find different probabilities, right? And so it's basically like converting it into a common language, kind of, is a way to think about it. And so how do we do this? Does anyone remember how we do this or what Z is equal to?
Is it like the P?
That's okay. So it's going to be like, if I have the probability that X, this random variable X takes on a value less than some value of X, right? Big X, random variable X, little x, certain value of X. Okay, just so that's clear. The probability of this, I can standardize it, which basically means I can subtract the mean and divide by the standard deviation. And that will turn it into a standard normal. And it's super cool. So you might see something like this. And this is little x, like I said. Z, this is Z, is like the random variable x. And you take away the true mean and or mu and the standard deviation. And so then we would just have like the probability that Z or some value is less than this other value. And that makes standard normal. So you'd see like standard normals always have a mean of 0 and or a variance of 1. So that's why if we look at, actually I can show you, that's why if we look down here at the standard normal PDF, which is this, and it's giving you the CDF values, right? Which is the area, right? Like we talked about. That's why you see that the mean here is 0. Because it's a standard normal. So that's pretty cool. Yeah. So that's how we standardize things. And so a few problems, we're going to practice using that table actually. So I think these problems, I just took them from your homework because I think your homework is actually very useful in helping prepare for the exam. So we'll just do a few of these and I'll kind of walk you through like how I go about them. If you have any questions, let me know. If you're given this problem, you need to find this. My first thing to do is like, okay, what kind of range are we talking here, right? So we want to find the probability that some value, Z value, which means it's standardized, is between these values. So if I have a mean of 0, that means like 0.3 might be like right here and 1.56 might be like right here. I want to find this, right? So using a CDF, how might we find that? And specifically using our CDF that looks at stuff above, not below the X value, I might want to take this and subtract it by this, and that'll get me just, oops, where's the undo? Oh, it's right here. That'll get me, that'll get me this, right? Which is exactly what I want. Does everyone see kind of how that works? So this would be f of 0.3 minus f of 1.56. And so we come over here. And so if z is 0.3, this is 0.3, it'll give us the area above it. So let's find 0.3 here. So the way this works is it gives you kind of like the first decimal place, and then this is the second two. Does that make sense? So if I want like 3.01, I would go find, or 0.31, I'd go here and here, and that would be this. Just in case you were struggling to read that, because I know I was when I first saw it.
Can you just say that again?
Yeah. So if I wanted to find like, if I'm looking for like let's do a different one. If I'm looking for like 1.47, I would come over here, find 1.4. And then these values up here, these are what give me this decimal place. So I'd find the 0.07, and wherever they like match, which is right here, is going to be the value I'm looking for. Yeah. So just going to erase all that. So 0.3, it looks like, is this. So 0.3821. And then the other one we wanted to look for, I think, was 1.56. I think. Let's see.
Yeah.
Okay, 1.56. So 1.56 looks like it's this one right here. So we'd subtract 0.382. We do that. 0.3821 minus 0.0594. And we get 0.3227.
Will this always be a positive number? Or will
The probability?
Yeah, or will there be times that it could be negative?
Yeah, your probability is always positive, right? Yeah. The Z values can be negative, right? The values that X can take on at random can be negative because it's just the value, but the probability of some range is always positive. It doesn't make sense to have negative probability, right? So there's an example, and then we'll just do one more that can trip people up sometimes. So if I have this negative in here, right, the probability is not negative, but this value. So I want to find 0. I want to find the probability that Z is between 0 and negative 0.9. So I want to find this, right? But that to me is the same, since remember it's symmetrical, is the same as this, like from 0. That's the same as from 0 to 0.9. So I might just find the probability that Z lies between 0 and 0.9, right? And what does that seem like to me? Well, f of 0 is going to get me all of this. F of 0.9, because if we remember on this standard normal table, it's giving us the probability above. It's going to give me all of this. So if I subtract the two, I get this range here. Does that make sense to everybody? So if you're thrown a negative your way, don't be startled. It's standardized, so it's the same across the mean, which is 0. Awesome. So let's see, what should we do next? I guess really quickly, we can talk about like if you're given a question like on your homework, like what's the 75th percentile, right? Or what's the 25th percentile? What's the median? The way we can think about those is the median is going to have 0.5 probability above and below it, right? Does that make sense? Because what is the median? It's just that middle number. If I had all the values and I just crossed them off on one end to the other, I'd arrive at the middle. That's the median. 75th percentile means that 75% percentile is that 75% lies below this X value. That's the 75th percentile. 25th, for example, that means 25% lies below. So this probability would equal 0.25. All of this probability would equal 0.75, right? And so what would I need to do if I have my CDF, right? I'm just going to take my CDF and set it equal to, if I want to find the 75th percentile, equal to 0.75. And I'd come down here and I'd look. You might be like, oh, I need to look for where I see 0.75 in the probabilities, but remember we're looking at the probability above. So if we're trying to find the 75th percentile using this table, what is the probability above this Z number that we need to look for? What is that equal to? 0.25, exactly. So I need this area to be 0.25. So I'm going to go here and look for 0.25. Looks like it's like right around here. Yeah. So I would say like 0.67, right? Has 0.25 above. So I'd say, oh, that's the 75th percentile of this standard normal. And don't fret if it doesn't equal exactly 0.25. It's very close. I would rather use this one than this one. But there might be some cases where they're like the same distance from the actual number. So it doesn't matter which one you use, but usually just do the one that's closest to whatever you're looking for, right? Yeah, I think this is like 0.014 off and this is 0.017 off. So that's why. Okay. So now that we've done that, that is standard normal, and that's kind of how to use the table for you. Any questions on that? Okay. One more thing about that. Let's say I had like some problem. I think on the practice exam, there's like a word problem that does this, which maybe we should just do right now. Why not? Because I actually think this was good practice with the table. But which one is it? Let's see. Also, there's a question like this on your homework that could be useful. Here it is. So question 3 on the practice exam says, if you want to pull it up, feel free. I'm not going to write it all out on here, but it says, suppose that BYU decides to rely on a new standardized test in making admission decisions. The university plans to admit everyone who scores in the 80th percentile or above. So I'm going to be drawing out my little PDF here to kind of make sense of this. So this would be like my 80th percentile, right? Whatever X value this is. So the it says the university plans to admit everyone who scores in the 80th percentile or above. So that's all these people, right? The cutoff score for admission is 510. So I know that this is actually 510. Okay. So the standard deviation of scores is equal to 90. And I know that X, or the scores, is normally distributed. What is the average test score? So this is what I know. And what do I need to find? The average test score. So I need to find this mu, right? So I know that 0.8, so the probability that this X value is below or equal to 0.8, if I take 1 minus this, that's the probability of those who are admitted, right? Or I mean, sorry, 510, not 0.8. 510 is equal to 0.8. Right, this section, well, would be equal to 0.2 actually. Right, because if 80% lie below here, that means 20% lie above 510. And so that means that 1 minus this probability that X is below that is equal to 0.2, because we know that this is going to equal to 0.8, right? So let's go to the table and let's find this 80th percentile, shall we? So we want 20% above. So we're gonna look here. Looks like that's like right here, 0.2005. Does everyone see that? And that's 0.84. So we're like, cool. We know that this is 0.84. So Z, right, if we're standardizing it, is equal to 0.84. This over here is not standardized, so we need to standardize it for this to be useful. And so if we remember, Z is equal to like the value of X minus mu over the standard deviation. We have Z, we have X, we have our standard deviation, and we're looking for this. How convenient. So let's plug everything in. 0.84 is equal to 510 is our X minus mu all over our 90. Multiply 0.84 by 90, 0.84 times 90. That means we get mu is equal to 434.4 is what I got. So that's an example of how like you can get like a word problem that requires you to think of the distribution, standardize it, and use that table. Without that table, you're not going to be able to solve this. So that's practice exam question 3. Any questions on that? Awesome. Okay, it looks like we might take like 15 minutes after 8. So just FYI. Okay, next thing is another practice problem from your homework. It tells us that X is normally distributed with a mean of 15 and a variance of 20. And it tells us Y is normally distributed with a mean of 10 and a variance of 30. So it's totally possible that you get some questions like this. So it asks you to find like, how is X plus Y distributed? So if we're given these questions, don't be afraid. All we're going to do is find the expected value, right, of X plus, or this is the expected value of X and this is the variance of X. And so all we're going to do is instead of for X, we'll do that for X plus Y. And so the expected value of X plus Y is just equal to the expected value of X plus the expected value of Y, right? Because it's a linear operator, I can split my expectation up when it's being added or subtracted, not multiplied or divided, right? X, common mistake here, X expectation of X times Y does not necessarily equal this. If it does, that might mean that we might be dealing with something that's independent, right? But that's not always the case. So just keep that in mind. Well, do I know my expected value of X? Yes, it's 15, right? I get that from here. Do I know the expectation of Y? Yes, that's 10. So I know that's 25. So the expected value of X plus Y is 25. So I know that X plus Y is normally distributed with a mean of 25. Now let's do the variance. So the variance of X plus Y is equal to the variance of X plus the variance of Y plus 2 covariance of XY. Another important thing to remember is if I have the variance of AX plus BY, for example, that's equal to the A squared times the variance of X, right? When I take a constant out of my variance, I square it, unlike my expected value, plus B squared times the variance of Y, plus 2AB times the covariance of X and Y. In this problem, it tells us that X and Y are independent, right? And so if something is independent, what is its covariance? 0, right? But if something has a covariance of 0, does that mean it's necessarily independent? No, right? It's not this biconditional thing. If it's independent, it has a covariance of 0. But I can have a covariance of 0 and still not be independent. So just keep that in mind. I could see that being like a true false question or something. But my variance of X I know is 20. My variance of Y is 30. I know that the covariance is equal to 0 because they're independent. So that means that this is just equal to 50. So I come over here, boom, X plus Y is normally distributed with a mean of 25 and variance of 50. Awesome, right? And then just one more we'll go through kind of quickly is if it's asking about the distribution of X minus Y. Well, I know that the expectation of X minus Y is equal to the expectation of X minus the expectation of Y, which is just gonna equal to 5, right? I take 15 minus 10. Cool. Means I know X minus Y is normally distributed with the mean of 5. Now let's do the variance. So the variance of X minus Y is equal to the variance of X. And right, remember that A squared is my constant. Technically, the constant is 1. So I'll just write that there so you're aware. But what's the constant for Y? Like, what is Y being multiplied by? What constant? -1, exactly. So I would need to add B, if B is equal to -1 squared. Which makes sense because you can't really have a negative variance because variance is squared. You can't have something that's negative as a product of a square, right? And once again, my covariance is 0. And so here, I know that my variance of X is 20 and this is 30. So if I do 5, or not 5, 20 plus 30, then I just get 50 again. So that means this has a variance of 50. So that's how you go about finding how things are distributed. If you have like 2 different distributions that are normally distributed, right? Random variable for X, random variable for Y. And if it gives you if some problem gives you some kind of combo of the 2, all you got to do is find the expected value of that and the variance of that. Use what you know about expected values and variances, right? This will be helpful in order to do that. So that is something that might be useful. And then last 2 things, which are, I guess, kind of lengthy, but is we have in continuous, if we're looking at continuous random variables, not discrete random variables, our joint density functions and our marginal density functions and our conditional density functions look a little different, right? And we solve them different ways. So I have this like practice problem I have that kind of goes through, I think, most of the questions you'll be asked. And it'll give you an idea of how to solve for these things. I would highly recommend looking at your class activity from this. like unit or this midterm span. And then also looking at the homework. I don't remember exactly which homework it was, but one of the homeworks, I think it was 9 maybe. One of the homeworks goes through kind of, you get a joint density function and then you have to find like the expected value of X. You have to find like the conditional distribution. You have to find the marginal distributions, right? And so I would highly recommend going through that too. But we'll go through a problem here and I'll go kind of fast, but let's say that my joint distribution is given by some PDF, right? Like this. And let's say X and Y are bound between 0 and 1. Okay. So I have this K here. And so you might get a question that's like find K, like your homework and your class activity. So what am I going to do first? How am I going to set this up? Does anyone know? Exactly. I'm going to integrate over X and Y. So that's where we see this double integration. And I'm going to make sure that this equals to 1. Because if it's a valid joint density function, the probability should equal 1, right? If we remember from what we know about PDFs, if we're integrating from one bound to the other, that's what's going to give us the probability, right? The area under that PDF. So let's just distribute this so it's easy to read when we take our integrals. And then quick kind of like interruption here, couple of tips. Hopefully those on the recording are still listening. I think these would be super helpful tips. Just make sure that when you're doing algebra, even if it takes a while, like you should have plenty of time on this exam. It's not timed. I would make sure and you go through just every algebra step to make sure, don't skip stuff in your head, because sometimes that can happen and you miss a negative sign or something goes wrong and then your whole answer is wrong. And then you miss a bunch of points just because of the algebra error, even though you know what you're doing. So I'd recommend going through every step, writing it out. Don't have to, it's my recommendation. And then another recommendation is when you're doing calculations on your calculator that are like kind of lengthy, like one thing I've seen a lot on like the homeworks and stuff is people will have the right setup up until the point where obviously they put it in their calculator and then they say it equals something that it doesn't, right? And it's just something with maybe like they input it in their calculator wrong, something like that. I know when I took this class in my homework group, almost always me and my partner always got different answers, even though we were plugging in the same numbers we thought. And just something happens a lot of times with calculations that can go wrong. So I would recommend just go through anything you're putting into the calculator, just do it twice, right? Especially if it's lengthy, and make sure you get the same thing twice. Be careful, be meticulous when you do that so you get the right answer. You will get partial credit if you have everything right up until that point, but the way it's set up, like the correct answer will give you like a lot of points. And if you don't get it just because of a calculation error, like I would hate for you to like have that, because it's not, it means that you just had a calculation error, but you knew what you're doing, right? And so that would be very unfortunate. So those are my 2 tips of advice to prevent, I guess, points that are missed very easily, right? If you're going to miss points, you want it to be because you actually didn't know what was going on, right? You don't want it to be because you typed it in the calculator wrong. So back to this. Let's integrate. We'll do X first. It doesn't matter which one you do first, right? Just FYI. So antiderivatives of this is going to give us kx squared minus 2 and then kx squared y squared all over 2, not minus 2, sorry. We're going to evaluate that from 0 to 1. And so that gives us k over 2, right? Because I plug in 1 for here, minus plug in 1 here, just ky squared over 2 dy, and this should all equal 1 still. So let's integrate that again. So ky over 2. Another common mistake is if there's no y here and I'm integrating on y, a lot of times you'll say like, oh, it's just k over 2, right? But remember, you got to add that y because the antiderivative of k over 2 is ky over 2. So don't forget to do that. It's a common mistake. Another common mistake is forgetting to multiply your denominator when you're taking the antiderivative, right? If I'm taking y squared to make it y cubed over 3, but I already have this 2 here, I need to make sure to multiply the 2. So don't forget and just have 2. That happens a lot. So sometimes I'll write it out like this just to make sure I'm being very cautious, right? And we're gonna evaluate that from 0 to 1. Why? Because our y bound is from 0 to 1. Hopefully this still equals 1. And then that gives us k over 2 minus k over 6, right? I'm plugging in 1 for here and here. That's the same thing as I'll put the common denominator here. This is the same as this. 2k over 6, because 3k minus k is 2k over 6 equals 1. Multiply a 6 over, divide by 2, k is equal to 3. Awesome. So now I know that my joint density function is equal to 3 times x times 1 minus y squared. Right? And I know that x and y are contained between 0 and 1. Cool. So that might be a problem you get. And then from there, it might ask you to find, might be like, well, find the marginal density function for x, find the marginal density function for y, right? And so, for example, the marginal density function for x generally is always going to be this. So like that's like your general formula. Sometimes sometimes students will have the question of, well, if I'm finding the marginal density function for x, why am I integrating over y? Like that doesn't make sense. Well, it's because when we integrate over y, it kind of like integrates out the y's, right? And if we have a function of x, what do we want it to be in terms of? X, not y. So let's integrate out the y, right? And have our function in just terms of x. So that's why we do it that way. So let's do that. So f of my marginal density function for x is just going to be 0 to 1. And these are going to be the bounds of integration for y, not x. Why? So many y's. Why is that the case? Well, because I'm integrating over y, not x, right? dy. So in this case, they're the same, but you might get a problem where they're different. So if I integrate this, I'm just going to distribute this out again, so it's easier to integrate. So that's 3x minus 3xy squared dy. So it's going to be 3xy minus 3xy cubed over 3, evaluated from 0 to 1. Okay. I plug in 1 for my y here and y here, and I get f of x is equal to 3x minus x, because these 3's cancel, which is the same thing as 2x. So there's my marginal density function for x. You might get a question that says, like, prove that the marginal density function of x is a valid PDF. So I actually haven't done that for this problem. I kind of made this one up. So let's see if it's valid or not. So the way we do that is we make sure it integrates to 1. Yeah, right? Because if it's not a valid PDF, that means the probability like of all the whole range is not equal to 1, which makes no sense. Remember, law of total probability is that it's equal to 1. So we want to make sure this equals 1. So we'll integrate from x. These are our x bounds. So integrate this PDF and make sure that this equals 1. So if we do that, we get 3x squared over 2 minus x squared over, oh, why did I do 3 minus x? Let's just do 2x. I don't know why I did that. Sorry, guys. Copied it down before I simplified it. So that's just going to be 2x squared all over 2, evaluated from 0 to 1. Okay. These cancel anyways, and I just get 1 minus 0 squared, which is just equal to 1. So awesome. That's a valid PDF. We just proved that. You might get a question that asks you that. Once again, I'm kind of just going through all the different kinds of questions you could get given a joint density function. Like I can imagine there being a problem that has like all, like a bunch of parts from the same joint density function, like your class activity. So here, let's find the joint density function for y really quick. So we're integrating from 0 to 1. These are the x bounds, right? So we'll integrate our joint density function. So that's just going to be 3x squared over 2, because I'm integrating over x, because I want to integrate it out to get it in terms of y. Evaluate that from 0 to 1. That just gets us 3/2 minus, plug in 1 here. That's 3y squared over 2, which is the same as 3/2 times 1 minus y squared. And here is my marginal density function for y. Another question you might get is, it's like, well, find the expected value of x or expected value of y. So it might be a little harder with y. So let's just do it with y. And generally, over here, I'll write the general, I guess, way you find the expected value in continuous random variables. Your expected value of x is just going to equal, and these are going to be your x bounds, x times your marginal density function for x, right? That's how you find the expected value. If we remember back to the discrete case, it was just summing all the different probabilities that x can take on times the x value, right? And so if we can kind of see the correlation here, right? We're multiplying an x value. Here we're adding up an x value. Here, this is what gets us the probability of some x equaling x, right? Our joint, or our marginal density function, is giving us those probabilities. Here, if we just had a probability distribution function like we used in discrete cases, that would give us the probabilities. So these kind of correlate. And then your integral and your summation kind of do the same thing. An integral, if you think about it like a Riemann sum, like it's literally just adding up all the different like infinite amounts underneath the curve, whereas the summation is just adding up all the different values you can take on. So similar, but this is with continuous, this is with discrete. Just to kind of clarify things in your head, if that was confusing for you. So if we do this, we're going to do integrate, and these are the y bounds, not the x bounds. So one thing I would make sure you have straight before you take the exam is, when am I integrating over the x bounds? When am I integrating over the y bounds, right? X time, or y, sorry, times my PDF for y, which is this, right? Or this. So that's just going to be 3/2 minus 3y squared over 2 dy. I'm going to just distribute that out so it's easy to look at when we take our antiderivatives. Now let's take the antiderivative. So we have 3y squared all over 2 times 2 minus 3y to the 4th all over 2 times 4, evaluated from 0 to 1. Also remember, ooh, I need to add more pages. So remember that I don't want this. Sorry, technical difficulties here. We're gonna add, I don't want to do that. What the heck? What the heck? Why is that not working? Okay, I don't know why that's not working. Just do this. Okay, it's being weird and glitching out. Okay, I don't know why it's doing that. But we're done with this anyway. So just remember that if this was not 0, I kind of have been like dropping it off, because if you plug in 0, it's always going to equal 0. But if this is not 0, if we remember, just make sure, I'll write it out this way on this one. Just make sure that you're still subtracting whenever you plug in this value into your whatever you're evaluating. So here it would be like 3 times 1 squared all over 4 minus 3 times 1 to the 4th all over 8 minus 3 times 0 squared all over 4 minus 3 times 0 to the 4th all over 8, right? And that would be what the integral equals. I've been dropping this off this whole time because we've only been working with a lower bound of 0. If it's not 0, You can't just drop it off. So just make sure you're plugging that in like we see here. So if we do this, we get 3/4 minus 3/8, which is 3/8. And there is our mean for y. So if I ask for the mean for y, we know how to do it. Last thing you might be asked on this is you could be asked like to find the CDF of this joint, given a joint density function, right? CDF for x, for example, but we kind of already went over how to do that. And then the other thing you could get asked is find like the correlation coefficient. So I apologize. I'm going to, actually, I'm just going to delete this. Problem solved. Okay. So if I want to find my correlation coefficient, remember we went over what it was equal to. It's equal to this. So I need to gather some important information. I need to get this and this. How can I do that? I can find the variances. So let's go through like finding the variance of y, for example. So the variance of y is just going to equal the expected value of y squared minus the expected value of y squared. They're different. Okay. So I have this, but I want to find this. So all I'm going to do is integrate from 0 to 1. These are the y bounds of y squared times my marginal density function for y instead of y. And if we do that, I'm just going to distribute this out real quick. So we get like 3y squared all over 2 minus 3y to the 4th all over 2. Hopefully that's what you guys have. And then we'll take our anti-derivatives minus 3y to the 5th all over 2 times 5. And this is going to be evaluated from 0 to 1. So if I do that, I'm just going to get 3 times 1 cubed, which is 3. 3 is canceled. I'm just going to get like 1/2 minus 1 to the 5th is 1 times 3 is 3 over 10. So I'm just going to get 3/10. That's the same thing as 5/10 minus 3/10, which is equal to 2/10, which is equal to 1/5. So I have my variance, or no, not quite. Also common mistake. Even I almost forgot, right? We found this, not our variance. So if we go back to our variance, it's going to equal 1/5 minus whatever we found over here. What is our expected value of y? I get lost. Is it that messy? Oh, I think it's 3/8, right? Is that what we said? Yes. It's equal to 3/8 squared. So I don't know what that is, but hint, we won't need it because this is an independent, x and y are independent in this case. But if I take 3 divided by 8 times 3 divided by 8, it's equal to like 0.140625. And so if I take 0.2 minus this, 0.140625, I get like this. And if I take the square root of that, that'll equal my standard deviation for y. And so that's how you would find this. Do the same thing for x, you'd find this, right? Last thing is we need to find the covariance. So do we remember how to find covariance? Anyone remember? From the beginning? We did do that, but that's not necessarily the covariance. Covariance is going to be the expected value of x times y minus the expected value of x times the expected value of y, right? Good news is we have this and we have this. Bad news is we don't have this. And so the way we'd find this is we would have to integrate our joint density function, because remember it's x and y. But remember when we take the expected value, we're doing whatever value of x or whatever the expected value is of times our function. So here we're looking at a joint density function because we're looking at X and Y. So this would be like XY times our joint density function, because this matches that, and this is because we're looking at X and Y. And then we do the same thing we've done before. We kind of just go through the integrals. This one usually takes longer because you're doing double integration. So I'll see if I can do this kind of rapidly, but I'm distributing out this XY to our joint density function, if we remember, was just this. Let's integrate on X first, because why not? Evaluate it from 0 to 1, because that's the bound of X. And that just gets us 1 in here, 3's cancel. That gets us just Y minus 1 goes in here, 3's cancel, just Y minus Y cubed, which is nice. Then let's take our antiderivatives, right? And then Y to the 4th over 4, evaluate it from 0 to 1. We plug in 1 here, we just get 1/2 minus 1/4, which is equal to 1/4. So we know E of XY is equal to 1/4. And then E of X we didn't do, but it's equal to 2/3. E of Y we did do is equal to 3/8. So our covariance, if it's equal to, like we said, E of XY minus E of X times E of Y, that's just going to be 1/4, right? Because that's what we found here, minus 2/3 times 3/8. 6 times over 24, hint, is 1/4. So 1/4 minus 1/4 is equal to 0. So our covariance is 0. Interesting. So the correlation coefficient would also be 0. But now we have this. And so if it was a non-zero number, we just take that number, right here, divided by these, which we can find, and that would be our correlation coefficient. And then the last question I can think of that you might be asked about this would be like, that you should prepare for, would be like, are they independent? Yes or no? Because I think that showed up on like your class activity. So really quickly, if this is equal to 2x we found, and this was equal to 3/2 times 1 minus y squared, and this is equal to 3x times 1 minus y squared. How do we check for independence in a continuous random variable sense? What's the formula for independence? What holds? Does anyone know? It'll be that the joint probability is equal to the probability for x and then for y. This will hold if independent, right? So let's see if they're independent. You might get a PDF, ask you to find the marginal density function. It'll be like, hey, let's actually like see if it's independent, prove if it's not, or if it is or not. So all you have to do is you take 2x, right? This is this times 3/2 times y minus y squared, which is this, which just gets me, this cancels with this, which just gets me 3x times 1 minus y squared, which is equal to this. So yes, x and y are independent. Fun stuff, right? Okay, and then the last thing with this would be like a conditional distribution. The formulas for that generally are like the conditional distribution of y conditional on x taking on some value. It's going to equal f of xy all over f of xx. So this is your marginal distribution or marginal density. And this is your joint density. It's your joint PDF, right? Similarly with x, it's just going to be this. And this is kind of an application of Bayes' rule, because if you remember, like the probability of A conditional on B is just equal to the probability of A and B. Yeah, thanks for coming in. Is the probability of A and B over the probability of B. So kind of the way we can denote this is this joint probability is the probability of A and B, or the probability of X and Y, all over just the probability of this, whatever it's conditional on, which in this case, for example, is Y. So therefore this, we're going to divide by the marginal density of Y, right? And so then we'd find some distribution, some function in terms of X and Y for this. And then if it said, well, find actually like the conditional probability of Y, but let's say X does have a value equals 10. And we'd say, this is what we're saying. We're like, oh, well, we just use whatever we found here, this density function, and plug in X for 10. And so then that would get us that answer, right? It'd be in terms of Y, because this is a density function of Y. And then another question you could get is like, what's the expected value of this? So the expected value of this is just going to be, right? Like we know, we're just going to integrate on our bounds. This is Y bounds of Y times, and then there's going to be a dy there, times whatever our density function for Y is, conditional on X equaling 10. And that's how we would find that expected value. And this should come out to a number. If you note, we're kind of integrating out the Y, integrated out. The X is being plugged in for a number, right? Which is 10 in this case. So we'll end up with a number. This, we will end up with something in terms of Y. This, we will end up with something in terms of X and Y, right? So that's one thing to kind of keep in mind. And that's conditional density functions. Not too tricky. And then lastly is kind of what we've been talking about like the last few days, is the idea of like sample. This is the last thing, versus population. So the intuition behind this is, let's say I want to find like the mean age in the United States. So in order to find that, like what would I need to do? I would need to literally ask or have data on the mean or on the age of every single person in the United States. And like Dr. Price mentioned, things like the census kind of attempt to find these true means or true population parameters, but it's imperfect because some people won't fill it out. Other things will happen, right? And so it's very, very difficult as researchers or as people to find population parameters. These are set values, right? The mean age is a certain value. It's not changing based at random. Whatever parameter of the population is some constant. So that's why we say like mu, for example, this is a population parameter. This is a constant. It's not a random variable. It doesn't take on random values. X bar is an estimator for mu. So what we say is, well, I can't go and ask everyone their age. Like that's not feasible. So what am I going to do? I'm going to sample random people across the United States, and I'm going to try to take the average of those. And hopefully that will be a good, accurate representation of what the true population parameter is. And that's your sample. So we use samples to try to estimate population parameters. So a common one that we talked about is X bar, right? It's a common estimator for population mean, and it's the sample mean. And so X bar is a random variable, right? Because X bar can take on random values, because if you remember in class, you had to like ask everyone like their ages, right? And then everyone reported their mean age of, or not age, the number of siblings everyone had, sorry. And then everyone had different X bars, right? It's a random variable because it's a function of random variables. It's totally random who I ask in the class, right? So that's kind of the idea between like sample versus population. So what we'll do is we'll use estimators, which are random variables, right, of like a sample for something to estimate a true population parameter, which is a set value, it's a constant. So we have different ways of evaluating how good are these estimators, right? If I am doing research for a professor and I'm like, oh, I came up with this functional form that estimates this true population parameter. I'm like, oh, I just came up with it. Like, they might be like, okay, well, like, I don't know how realistic this is, but like, okay, let's check to see, is it biased? Is it consistent? Is it efficient? And those might be good characteristics to look at to evaluate how good is my estimator, right? And so a good estimator is going to be unbiased. So we might, if we have an estimator and we want to figure out like how good it is, the first question we'll ask is it biased? And so that brings in like this bias formula. Let's say theta hat is some estimator and theta is the true parameter or true population parameter, right? So theta is a certain value, certain constant value. And so my bias is just going to be the expectation of my estimator minus the true parameter, which makes sense intuitively, right? I'm saying, well, what do I expect to get from this estimator? If this estimator is some distribution, random distribution of a random variable, I pick one value, like what do I expect it to be? If I expect it to be the true population parameter, then that's great. There's no bias, right? I'm getting the same, I'm expecting to get the same thing as it actually is. And what am I trying to do with an estimator? I'm trying to get this true population parameter. That's all an estimator is doing. And so the bias is going to be the difference between the two. So if we remember like the bias of X bar, for example, is 0, right? Because the expectation of X bar is mu. And when we subtract off the true mean, it just equals 0. So that's an example of an unbiased estimator. If I go and I find the expected value of some estimator, if it's like, oh, theta hat is equal to, I don't know, X, or sorry, theta minus N over N or something. I don't know if this is biased or not. We could look, but we won't because we don't have a lot of time. If I took the expectation of this, if it were unbiased, that means this would have to equal this. And if it doesn't, then that difference, that amount is the bias, right? So that's one thing we can do is it biased? Second question we can ask is it efficient? Okay, so I can't look at efficiency of one estimator or random variable on its own. I need another one, right? Because efficiency is a comparison. Yeah, we follow that. So if I say like the variance of theta hat 1 as one estimator is less than the variance of theta hat 2, which one is more efficient? I'll ask you guys. If this is the case, is theta hat 1 or theta hat 2 more efficient? Theta hat 1, right? Because it has a lower variance. The spread of the data is less. So that means each observation is closer to the true mean more of the time, right? It's like I could have a variance that kind of like looks like this or a variance that looks like this, right? And I want the one with the lower variance. So this is more efficient. So that's efficiency. We probably, if we are coming up with some estimator to find some true population value, we probably want a good efficient estimator. And then the third thing we can ask is it consistent? So that just means as my sample size or N gets bigger, as it approaches infinity, I need one requirement is that the bias of my estimator, so in this case, we're using theta hat as our estimator, needs to approach 0. And the variance needs to approach 0. So that means as I get more observations in this estimator, as I pull out at random more values that this estimator is distributed by, am I getting, like, is the bias becoming 0? Am I getting the true parameter, like, more of the time? And that's the same thing as the variance. Like, is it getting less, like, a variance equaling 0 means you're just getting values that are all the same. Like, am I getting more consistent? Am I over time, right? So it's just as I increase N, is it getting, is it consistent? Means is the bias approaching 0 and is the variance approaching 0? So if it's asking you if some estimator, it might give you some estimator on a question like, oh, theta hat suppose it equals, I mean, we can use the same thing that we did over here. Suppose it equals this, right? If I take the variance of this, and if n is in the denominator, for example, that means like infinity in the denominator means that it's going to approach 0, right? That might be like, oh, yes, the variance is approaching 0, or the bias, I can solve that out and see if it's approaching 0. And that's how I would know it's consistent. Make sure you check for both those conditions, not just one. And those are like the 3 different things that we can look at when we're trying to evaluate how good is an estimator, right? And then the last thing is kind of like what we talked about today. And then actually one quick thing that I think might be helpful. Like one thing to note is this is true, but if we take like for X bar, for example, this kind of goes into what we talked about today. Oh, this should be variance. It's not equal to sigma squared, but sigma squared over n. So today we kind of talked about like, as I increase the number of observations or the amount of X bars I'm pulling, right? I'm getting more of a normally distributed curve. So even if X is distributed along a uniform distribution, like we did today when he did that simulation, as I keep taking more and more and more samples and take the mean of those will become normally distributed. So the definition, that by definition is the central limit theorem, like we talked about today. So you could totally have a question that might ask you like something about what is the central limit theorem, or define the central limit theorem, or why is the central limit theorem like applicable in this case, right? And so that is kind of what we talked about today, that any estimator that is large enough will be normally distributed eventually, right? And so that's something important to keep in mind. We looked at like the variance estimators and the mean estimators, and we looked at how to make S squared instead of like sigma, or instead of the expectation of X bar. And that was just like the proof he did to show that that variance estimator is biased. So we need to subtract 1 right there on that end. Like he said in class, you won't be expected to do that whole proof, but it would be important to understand what's going on. So, and that's about all I have for you guys. Feel free to head out. I might just, for people on the recording, go through the true or false from the exam just really quickly. But thank you for coming. And if you want to stay for that, you can, but thank you for coming. And hopefully that was helpful. Good luck on your exam. You're going to kill it. Definitely prepare. Studying goes a long way. So thanks for coming, guys. Bye. Okay. So lastly, I just wanted to go through really quickly, like the true or false, on the exam, practice exam. So if you have that pulled up, that would be great. I think true or false can sometimes be the most tricky. So we'll just go through this really fast because I don't want this recording to be like super long, but feel free to put this in 2 times speed. I mean, this is towards the end, so you wouldn't have heard that in the beginning anyways. But first true or false question. If X and Y are random variables with a correlation of rho XY, then the correlation, it asks here, it's like the correlation of 2XY is equal to 2 rho XY. Well, if you remember earlier in this recording, we said that that doesn't matter, right? That this is actually equal to just the correlation of XY. You can check out, like, it's because like the variance is scaled also. And so since the variance scales the same way like the covariance scales, like it doesn't matter. Because if we remember, our correlation coefficient is just going to be this, right? So this is false, right? Question 1 is false. Feel free to look at like Dr. Price's lecture notes or the key on this exam to see kind of the math behind that. Next, it says, is this function a legitimate density function? I would venture to say yes, because this kind of looks like a uniform distribution, right? With A and B being -1 and 0, right? And if we were to kind of integrate this, we would get 1, right? And so the probability, this is 1. -1. I guess this is bad. -1 and I guess it should look like this, huh? -1 and 0, and this is 1. This should equal 1. So that seems to be good. True. Awesome. The next is question 3, or I guess 1C, is if random variables x and y are independent, then for any y, the conditional mean of the expectation of x conditional on y is equal to just mu x. So let's remember that this is equal to our joint density function over whatever the second one is, which is y. So that's our marginal density function for y. And then if we just kind of, it says in this problem, if random variables x and y are independent, let's remember that independence means that this holds, right? So if that's the case, then I can kind of rearrange things here to say that this is equal to f of, or my marginal density for y and my marginal density for x divided by, like we have up here, my marginal density for y. These cancel, and that's just equal to this. And so if I were to take the expected value of this, remember our expected values is going to be like the bounds. So I'm not sure what the bounds are here, but the bounds of x in this case times the value of x times whatever our conditional probability is. Right? And if we know that this equals our marginal density function for x, which is shown by this over here because these cancel, right? Then we can confidently say, oh no, here's some work from stuff before, whoops. Then we can confidently say that this is equal to x times this. And if we remember, e of x is just equal generally, these are going to be my bounds for x, of x times my marginal density function for x, integrating across that. And that's exactly what I have here. So that means this is equal to this. And we know that this is equal to mu x. And so yes, looks like this is true. Great. Oh no. And then 4, or D, it says if z is normally distributed and z is equal to 1.285, it's stating that this is the 10th percentile. Well, if we go to our handy dandy table that I deleted off of here, unfortunately, hopefully you can pull that up. We see that the 90th percentile, remember, is this, meaning that 10% is going to lie above. So in our table, we want to search for where 10% lies above. Or not 90th. Sorry, we're looking at the 10th percentile. So this is my 10th percentile, meaning 0.1 lies 0.1 lies below, meaning that 0.9 lies above. So I would want to find, since the table shows probabilities above, I would want to find this right here, to wherever it equals 0.9. And if I go on the table, that is not 1.285. And so therefore it is false. And then E, it basically says that an estimator theta hat is consistent, then it is also unbiased. This is false because you can have an inconsistent estimator that is biased or a unbiased estimator that is not consistent. So since consistency requires that it just like over time the bias is equal to 0, that could mean that the bias isn't equal to 0, but as you increase your sample size, it approaches 0. So that means that it could be consistent but biased, which means that this would be false. And I think those are all of those true false questions. Thank you everybody for watching. Thank you everybody for coming. I'm going to go ahead and end this now.